All right, so we're going to work through the examples given on slide 36 of lecture set number 7. So we continue with our illustrations of computing confidence intervals, but this time we're going to be working in a situation where the standard deviation of the population, that sigma value, is no longer given to us. And this is going to change slightly how the interval is constructed. Okay, so what is the situation? We have, from a simple random sample of size 6, an estimate of the mean theoretical spring constants for type 1 springs is x bar equals 2.03 with s equals 0.068. Assume a normally distributed population. Okay, part A, compute a 95% interval from mu. So the assumptions here are the same, except we're going to be missing one piece. Okay, so we start off assumptions. So we have a simple random sample that's told to us we require x bar is normal. Okay, this is also given because we are told it's a normally distributed population. So if it's a normally distributed population, x bar has to be normal. And now we have sigma known. Okay, well, this is no longer true, right? We don't have sigma. But this isn't a problem. It just means that the interval is now going to be based off a t-value rather than a z-score. Okay, so we're going to have 95% CI. Step 1. Okay, we have t subscript alpha over 2, comma n minus 1. So this is t 0.05, comma 6 minus 1. Comma 6 minus 1, and this is t 0.025, comma 5. Okay, now I skipped one step here, which is where I found alpha. You'll remind yourself that alpha is 1 minus the confidence level. Okay, so we've seen a lot of examples of this already. It's a 95% interval. Alpha is 1 minus 0.95. All right, now what we have to do is we go to our t table, and we're going to match 0.025 to 5. Okay, so we go to our t table, 0.025, 5, 2.571. Okay, so we come back here, 2.571. All right, now we have on step 2, x bar plus or minus t alpha over 2 n minus 1 multiplied by s over the square root of n. Okay, so this is going to be 2.03 plus or minus 2.571 multiplied by 0.068 over the square root of 6. So that's 2.03 plus or minus 0.071. And that gives us 1.959 to 2.101. Okay, and now we would just say we are 95% confident that the mean TSC of type 1 springs is between 1.959 and 2.101. And so you can see that the process here is actually, it's exactly the same as what we had in the case that sigma is known. But because sigma is unknown, we now use a t-value instead of a z-score. And where the sigma was located before in the confidence interval, we now replace that with little s, which is the sample standard deviation. All right, so part B, does the interval in A give evidence to suggest that the mean TSC for type 1 springs is greater than 1.9. Explain. Okay, so our interval in A is 1.959 to 2.101. So we have 95% CI is 1.959 to 2.101. Okay, so this is telling us that based off of our calculations, we're 95% confident, as we just wrote out, that the population mean TSC for type 1 strings is between these two numbers. Since the lower bound, 1.959, is bigger than 1.9, this gives evidence that the mean TSC is greater than 1.9. Okay, said another way, since all the values in the interval are greater than 1.9, we have evidence that the mean TSC is greater than 1.9. So since all values in CI are greater than 1.90, we have evidence that the mean TSC is greater than 1.90. Okay, so pretty straightforward in that sense. We just take the value of interest, which is 1.9, and we compare it to the interval. In this case, all the values in the interval are bigger than 1.9. So that means that there's evidence that the mean TSC is greater than 1.9. Okay, part C, compute the margin of error for a 99% CI about mu. All right, so as we have shown before, the computation of the margin of error, it depends on the same assumptions as the confidence interval, right? And nothing's changing here for us except that the confidence level has gone up to 99%. So we would just say 99% margin of error. We'd have step 1 here. Okay, so now we're going to have alpha is 1 minus 0.99, which is 0.01. So we're going to have t 0.01, or t alpha over 2 comma n minus 1 is now t 0.005 comma 5. Okay, so that value is going to be from the student t table a value of 4.032. So we still have 5 degrees of freedom. We've just changed our area to 0.005. So now the t value is 4.032. Right, like this. Okay, so then we would have the margin of error is our t value multiplied by s over the square root of n. So this is 4.032 multiplied by 0.068 over the square root of 6. And that gives us 0.112. Which interval is more accurate, the 95% or the 99%? Explain. Okay, well, we can say the 95% CI is more accurate than the 95% CI because the margin of error for the 99% CI is greater than the margin of error for the 95%. See that. So that same idea that we had talked about earlier, that comes, that's the idea of accuracy, again, doesn't change with the z-score versus t-value. The closer the two bounds are to each other, so the shorter the interval is, the more accurate it is. In this situation here, the only value we're changing is the t-value that corresponds to the confidence level. So our t-value went from 2.571, I believe it was, up to 4.032. You're multiplying by a bigger number, so the margin of error gets bigger, which means that you're adding and subtracting a bigger number to the sample mean, which means that you're creating a longer interval. As always, if you have any questions, please let me know.